Hey everyone, this is John Buck back with another continuous time linear systems video. In this video we're going to talk about block diagrams for continuous time systems. Similar in a lot of ways to what we saw in discrete time linear systems, but there's one important change. One thing that's different and then another change in strategy. So we think if I have a system described by a differential equation. A lot of the systems we want to build in continuous time, our systems are described by linear constant coefficient differential equation. Or we'll abbreviate them because it's just a lot to write as LCCDEs. We need, for the systems described by these kind of differential equations with our initial rest condition to make them causal and LTI. We really need three blocks in or three parts to build one of those differential equations. And at first glance, the obvious answer, well, pause the video for a minute and think if you could think of the three parts I would need. Right? One is a gain or scalar. Right? Something to scale a signal by a constant gain. Right, so when I do that, I'll represent it to say I've got x coming in. I'll just have an arrow with some branch gain c next to it, so y would be c times x. Another piece will be an adder. Right, that I have two signals coming in. And add them to get out a new signal that's the sum of those two. And the third thing we need to make a differential equation is a derivative. So that's the obvious answer. And maybe the one that discrete time system sets us up to expect, right? That if I'm looking for a derivative, I put x of t in to a derivative box, a block that takes derivatives. To have dx dt. And while that makes a lot of sense, it actually turns out that it's really generally not a good way to build engineering systems. We actually try pretty hard to avoid this, even though it's the obvious direct thing. We say, what are you talking about, John? We've got a differential equation is an equation built out of derivatives. How are we supposed to make one without derivatives? Well, the trick is that instead of doing it with derivatives, what we use in practice are integrators. And there are a bunch of reasons for it, but integrators tend to be more stable, and particularly a derivative amplifies any background high-frequency noise that's always hanging around in real systems, whereas integrators help us remove noise by taking the integral over time. Really random things get reduced. And so we end up, instead of using derivatives, we find ways to manipulate the equation to use integrators instead. And so what I have here, technically these are an integral from minus infinity up to t, so my output at any time is a running total integral of the input signal up to t. So because of this, it takes a little more practice to make block diagrams or to think about how am I going to massage the equation to get something that I can write using integrators instead of just the obvious derivatives by reading off the equation. So let me show you an example of how that works. Let me set this up on a new page. So suppose I want to draw a block diagram representing a system to implement the causal LTI system. A causal LTI system that satisfies this differential equation. So that dy dt plus 3y of t equals 2x of t plus 4 dx dt, right? Where x is the input and y is the output. Well, first of all, just to practice, what ordered differential equation is this? You can pause the video and think about it for a moment and come back. If you want to help the ed, you could put it in the comments. I guess that's what they say on videos these days to try to boost their videos. I'm not too fussed about that. But I do notice how often people are trying to get you to put things in the comment to boost their videos when I watch other videos on YouTube. Okay. So hopefully you're back. This is a first-order differential equation, right? This is first order because the largest derivative on either side is a first-order derivative. And so the key to finding block diagrams from differential equations is to solve the differential equation to get the highest derivative of y alone, or usually y, sometimes x, but the highest derivative alone on one side. And if it's a tie, get the y alone on its side. So here we have first derivatives of both y and x. So I'm going to solve for dy dt as my first step. Right, so when I do that, I move this over to the other side, and I get this equation here. I have minus 3y of t plus 2x of t plus 4 dx dt. And the reason this sets me up now is that if I integrate both sides of this equation, on the left-hand side, I'll have the output y of t in terms of things that are either the inputs themselves, the output itself, or integrals of them. So things I can feed into integrators to get my answer. So let me see what happens when I take the integral of both sides now that I've done this. I'm going to sort of put this in a different color to remind us that first I solved to get dy dt alone, and then I'm going to take an integral of both sides. And when I do this, the first term on the left-hand side just becomes y of t. Then on the right-hand side, I get the integral of y and x, and I'm going to put those together inside the same integrand. Okay, so I've done them in terms of the dummy integration variable tau here because I've got a running integral. This is, I guess, the integral from minus infinity to t. And then on this last term, when I take the integral, it cancels the derivative, and I get a 4x of t. So now this sets me up to write my output in terms of combinations of things, feeding in inputs and outputs going into an integrator, plus another version of the output of the input. So the way, again, I often do this like we did in discrete time linear systems, I often set up by putting the input on the left-hand side, the output on the right-hand side, and sort of fill in the blanks almost like it's a little mathematical crossword puzzle as I work. All right, so if I were going to do this, let me scoot this up to make some room. So I would look at this and say, well, I have an integrator that needs to take 2 times the input and minus 3 times the output. So let me put my integrator here in the middle and say, what do I want to go into that input? Well, it's a sum of 2 things. I need to take 2 times the input, and then I need to take a feedback branch to bring the output back here. And while I'm bringing it back, I need to scale it by minus 3. Right, so that when I do that, I can label these branches going into the integrator. So I have minus 3y of t on the bottom branch, and 2x of t on the upper branch. So the output here of this adder is 2x of t minus 3y of t. So computing that integral gives me everything up to here, right? The output of that integrator gives me this term for y of t, and I would just add in 4x of t to that. So I want to grab my x of t. So I'm going to sort of sneak it through here. I should have left myself a little more room. And so I'm going to need an adder here where I'm going to take the output of the integrator, and this branch has a gain of 4, right? So what's coming through here now is 4x of t, right, on this branch. So I'm taking 4x of t, which is this piece here, and adding it to this integral, right? This term here is what's coming out of this integrator. So I've got this 2 pieces, add them together, and that gives me y of t, which again keeps getting fed back into this integrator. So this is how I would design a block diagram of a system to integrate this. I would take my input, scale it by 2, feed back my output minus 3, run it through my integrator component, whether that's a circuit or a piece of software, and then add 4 times the input directly to the output of that integrator to give me my output going forward. So loosely similar to things we saw with the difference, the main trick you need to remember, or not trick, but change, is that instead of writing things in terms of delays, you'd think, oh, well, we'll just use derivatives instead of delays because we're doing differential equations. And in theory, you could make those and we could draw those diagrams, but they're not practically the way we want to build systems down the road. We want to build them with integrators because they're just electrically more stable to do that. Okay, so let me go finish up with the credits. But again, this video has covered basics of block diagrams for continuous time systems that are implementing linear constant coefficient differential equations. The key thing is solve for the highest derivative in terms of y, and then just take integrals until you get y of t alone on the left-hand side. It's a little trickier when the highest derivative is x of t. We're not going to worry about that as much first. Handle the case where the y's are the higher derivatives first to get some practice with it, and then maybe we'll come back to the later what happens when x has higher order derivatives than y. All right, well, that's all for this time. I'll see you in my next video.